Okay, let's dig into this. Imagine a future where driving is genuinely safer, far more efficient, and, a lot less stressful. That's the exciting promise of self-driving cars, isn't it? Companies like Tesla have even put out their own safety reports, painting a pretty compelling picture, significantly lower accident rates for their autopilot system.
What's truly striking here is the sharp contrast between that enticing promise and the often sobering reality. Because while those claims are out there, the U.S. government's National Highway Traffic Safety Administration, NHTSA, has actually launched multiple ongoing investigations into Tesla's autopilot and full self-driving, or FSD, systems.
Right.
And we're talking hundreds of accidents, serious injuries, and tragically, a number of fatalities. And these aren't just, isolated incidents. The investigations highlight disturbing patterns, like Tesla's colliding with parked emergency vehicles or serious crashes happening in challenging low-visibility conditions.
So, for you, our listener, our mission for this deep dive is to really explore a fundamental gap that exists. It's the space between the perceived intelligence of Tesla's automation and the absolute non-negotiable demands of real-world road safety. And this isn't about one tiny software bug. It feels more like systemic issues that weave through the hardware, the AI itself, and even, well, human psychology.
That's a good way to put it.
We're going to break this down into 4 key gaps to help you truly grasp what's happening on the road, what it implies for the future of driving, and how you perceive these powerful technologies. We'll start by looking at the words we use, then dive into what the cars actually see, then grapple with the AI's common sense or lack thereof, and finally understand the human element.
Okay, let's kick things off with a crucial baseline: understanding what these systems truly are. As many of you tuning in probably already know, the Society of Automotive Engineers, or SAE, sets the global standard for driving automation.
Right, the SAE levels.
Exactly. This standard, J38016, defines 6 levels: level 0, human does everything, up to level 5, full autonomy. The critical distinction for us today, the one that really matters for our discussion, is that line between level 2 and level 3.
Okay.
These levels clearly spell out who's actually in charge of the dynamic driving task, steering, accelerating, braking, and who's responsible for object and event detection and response, basically watching the road.
And that level 2 to level 3 distinction is absolutely vital, isn't it? Because that's where the responsibility for continually monitoring the driving environment actually shifts.
Precisely.
At level 2, the human driver is still fully responsible, full stop. But at level 3, the system takes on that monitoring responsibility within its specific operating conditions, though the human still needs to be ready to jump back in. It's a huge difference.
A massive difference in liability and expectation. And here's the unavoidable reality check for Tesla.
Yeah.
Both their autopilot and full self-driving supervised systems are, without question, SAE Level 2 systems.
Unequivocally level 2.
Yes. Tesla's own manuals are quite explicit about this. They state drivers must remain fully attentive, hands on the wheel, ready to take control at any moment.
So any terms you might hear like L2+, that's just marketing.
It's marketing speak. It doesn't change that fundamental responsibility. It's still level 2.
It's fascinating how much power words hold, especially in tech, right? When you hear autopilot or full self-driving, what's the immediate impression that creates, and how does that square with the technical reality?
Well, that's the core of what we're calling the terminology gap.
Yeah.
It's so significant that the SAE standard itself actually advises against using names like self-driving for systems below level 3.
Really? They specifically say not to.
Yes, precisely to prevent this kind of confusion and, frankly, to maintain public trust.
And this semantic gap, this difference between the name and the reality, it has very real, sometimes tragic consequences.
Absolutely. It often leads directly to overtrust and what's known as automation complacency, which is something we'll definitely get into more detail on later.
Sure.
We've seen it play out. For instance, there was a lawsuit in China where a victim's family specifically aimed to highlight the, quote, flaws in the tech and urged Tesla to be much more careful in its marketing, to not just use self-driving as a catchy selling point.
And NHTSA sees this too.
Oh, yes. NHTSA's own investigations have consistently concluded that foreseeable driver misuse is a significant factor in many crashes. And this misleading terminology plays a direct role in enabling that misuse.
So next time you see that full self-driving badge, the crucial thing to remember is what it actually does versus what the name implies. It definitely doesn't mean kick back and relax.
Not at all. You are still the driver.
Okay, so if the words themselves are causing confusion, what about what these cars actually see? That brings us to our second big challenge: the sensor gap. And Tesla's made a very unique, some might say risky bet here.
They certainly have.
Unlike most competitors who combine cameras with radar and LiDAR, Tesla has gone all in on vision only, relying solely on cameras.
Mm-hmm. They even removed radar and later the ultrasonic sensors from their cars, promoting Tesla Vision as somehow superior. Elon Musk has used the analogy, humans drive with eyes, so cars should too.
But isn't the human eye also limited by bad weather, fog, heavy rain? What's the fundamental difference that makes cameras uniquely problematic here beyond what we already experience as drivers?
That's a great question, and it really boils down to the physics of perception. Cameras are passive sensors. They need existing light.
Right.
So their performance is directly tied to the quality of that light. If it's dark, if there's glare, if something's blocking the lens, they struggle. Radar and LiDAR, though, they're active sensors. They send out their own energy radio waves or laser pulses and measure what comes back.
Ah, okay, so they make their own light, essentially.
In a manner of speaking, yes. And that fundamental difference exposes the camera's inherent weaknesses.
And those weaknesses are pretty significant, right? I mean, even Tesla's own manuals admit autopilot features tend to perform poorly in heavy rain, snow, fog, hail.
Exactly. And cameras also struggle in low light or at night, when facing direct glare from the sun or oncoming headlights, or even if their lenses are just dirty or covered in mud.
So think about how cameras work. They're great at identifying things, right? Like recognizing a stop sign shape or spotting a person.
Correct. They excel at classification.
But they're not so great at judging how far away something is, especially when conditions aren't perfect.
Precisely. They see the world somewhat like we do. But crucially, without our brain's incredibly sophisticated processing power to interpret ambiguous situations or fill in the gaps caused by poor visibility. Radar, on the other hand, it just punches right through rain and fog to give you pretty accurate speed and distance data. Even if the image isn't sharp, it knows something's there and how fast it's moving.
And LiDAR?
LiDAR is like building a highly detailed, constantly updating 3D map of everything around the car. It's incredibly precise for shade and distance, though historically it's been more expensive. The point is, they all have different strengths and weaknesses, but only one type of sensor is completely dependent on perfect visual conditions.
And this isn't just theory. We have documented independent tests showing this. Didn't Mark Rober do a test on this?
Yes, that was quite revealing. His test showed a Tesla Vision car completely failing to detect a pedestrian dummy in simulated fog and heavy rain. It even crashed into a painted wall illusion.
Wow. And the comparison vehicle?
A LiDAR-equipped Lexus. It stopped safely in every single one of those challenging scenarios.
That starkly illustrates the difference.
It really does. And it makes you ask, if our own human eyes struggle in bad weather, why would we assume cameras alone would be sufficient, especially without that human intuition and influence?
Plus, you mentioned NHTSA is looking into this specifically.
Yes. Recent NHTSA probes into FSD are targeting accidents that happened in low visibility conditions, things like bright sun glare, fog, even dust clouds, including, tragically, fatal pedestrian incidents. This isn't just anecdotal.
And what about phantom braking? Is that related?
It's strongly linked. Those sudden, scary, seemingly inexplicable braking events on highways. Reports suggest vision-only systems are more prone to this, potentially misinterpreting things like shadows under bridges or even large billboards as imminent threats.
So the key takeaway here seems to be that Tesla's vision-only approach isn't just a software setting. It's a fundamental hardware limitation. It's a bet against physics that directly impacts safety in common, yet challenging, real-world conditions.
That sums it up well. It's a design choice with very real physical limitations, not just code that can be easily patched.
Okay, let's move to our third area, what we're calling the common sense gap. This gets into a fundamental challenge for all AI, really, dealing with edge cases.
Right. Edge cases are those rare, unusual driving situations that fall outside the massive data sets the AI was trained on. They're the unknown unknowns for an AI.
Scenarios where the usual patterns just don't apply.
Exactly.
And these aren't just theoretical problems for engineers, are they? We're talking about real things, like a sofa falling off a truck on the freeway.
Or a pedestrian suddenly darting out from behind a parked van. Or an unexpected, poorly marked change in a construction zone. An animal running across a dark road.
Things human drivers often react to instinctively, even if they've never seen that exact thing before.
Precisely. Now, Tesla's approach is heavily data-driven. They collect billions of miles of anonymized driving data from their fleet worldwide. The idea is the system learns from sheer volume, including those once-in-a-lifetime scenarios.
And FSD V12 uses imitation learning too, right? Learning from their best drivers.
Correct. It tries to mimic how skilled humans drive.
So here's the paradox for me. If it's seen billions of miles, if it's learning from the best human drivers, how could it possibly miss something that seems obvious to a person, like that sofa on the road?
That is the paradox. While this data-driven approach makes the AI really good in common situations, driving smoothly, handling typical traffic, it creates this total reliance on past data. It learns correlations extremely well.
But it lacks, what? Real understanding.
Exactly. It lacks genuine common sense, that tacit knowledge, contextual awareness, and causal reasoning humans use. We can infer things. We understand why things happen. A human driver seeing a car ahead swerve erratically might anticipate an unseen obstacle and start braking before they even see it. An AI, if it hasn't learned that specific pattern means danger ahead, might just keep going until the obstacle is directly in view, which could be too late.
And this common sense deficiency, as you call it, isn't just theoretical. It shows up in the accident reports, doesn't it?
Tragically, yes. Let's go back to that pattern of Teslas on autopilot, hitting parked emergency vehicles, even with flashing lights. That's a classic edge case. A large, stationary object unexpectedly in a travel lane. Highly visible, but unusual.
But couldn't you argue that humans aren't perfect in edge cases either? Maybe these systems are just reflecting how hard unpredictable situations are for anyone.
That's a fair point. Humans make mistakes, absolutely. But the reason for the error is often different. A human might be distracted, fatigued, or make a poor judgment call. The AI, particularly a data-driven one, might fail because it literally hasn't encountered enough similar data to form a reliable pattern, or it can't generalize the concept of a large stationary object in road stopped from other contexts. It lacks that abstract reasoning.
So it's a different kind of failure.
Often, yes. We've also seen documented issues with Tesla systems handling crossing traffic, especially big trucks, leading to fatal crashes. There was that incident in China where a Tesla didn't detect a partially parked road sweeper after the car ahead swerved to avoid it. The AI didn't seem to interpret the preceding car's swerve as a warning signal like a human likely would.
And Tesla even acknowledges some of this.
Their own manual admits FSD may struggle with, and I quote, rare objects such as trailers, ramps, cargo, open doors, etc., protruding from vehicles. These are exactly the kinds of edge cases we're talking about.
So what we're really saying is an AI can seem incredibly smart in 99.9% of driving situations, maybe even smoother than many humans, but then be catastrophically dumb in that critical fraction of a percent where true understanding, inference, and common sense are required. And that tiny fraction is where lives are on the line.
That's the heart of the common sense gap. It's not about average performance. It's about reliability in the face of novelty.
Okay, our fourth gap gets a bit more technical. The interpretability gap, sometimes called the black box dilemma. With full self-driving version 12, Tesla made a pretty big shift in how the system works internally, right?
A very significant shift. They moved away from a more traditional modular system, one that had distinct software components, often written in C++A, for things like perception, prediction, planning.
Stuff engineers could look at and understand the logic.
Exactly. They moved towards a single, unified neural network.
An end-to-end system.
That's the term. This system essentially takes the raw data from the sensors, mostly pixels from the cameras, and directly outputs driving commands. Steering angle, acceleration, braking.
And the goal is to imitate human driving by learning from huge amounts of video.
Yes. Rather than having engineers try to hand-code rules for every conceivable situation, the network learns the mapping from input to output by watching humans drive.
So here's another paradox. Users often report this new system feels more human, maybe handles complex scenarios more smoothly. But you call this the end-to-end paradox. Better performance potentially coming at the cost of safety and reliability. How does that work? If it performs better, isn't it safer?
Not necessarily, and that's the tricky part. This connects to the bigger picture. How can we truly trust a system if we don't fundamentally understand why it does what it does? That's the black box problem.
Because the decisions aren't based on clear rules anymore.
Precisely. Because the decisions emerge from the complex interplay of millions or billions of parameters within the neural network, it becomes incredibly difficult, sometimes impossible, for engineers to pinpoint why the system made a specific mistake.
Like, why did it suddenly break for no reason, or why did it fail to see an obstacle that time?
Exactly those kinds of questions. This lack of transparency or interpretability makes systematic debugging incredibly hard. You can't easily find and fix the root cause if you don't understand the cause. It also makes guaranteeing consistent, reliable performance very difficult.
And that lack of understanding also affects updates, right? You mentioned performance regressions.
Absolutely. With these complex end-to-end systems, when you train the model with new data to fix one specific problem, you might inadvertently break something else that was working fine before.
So you fix one thing but cause another issue somewhere else.
It can happen. It becomes really hard to lock in correct behaviors across the board. This opaque nature also turns verification and validation V and V, which is absolutely critical for any safety-critical system like cars or planes, into a nightmare.
How can you rigorously prove it's safe?
It's extremely challenging. How do you guarantee its performance in edge cases it's never seen before if you can't inspect its internal logic? There's also the risk of causal confusion. The AI might learn a correlation, like red brake lights usually mean the car ahead is braking,
Okay, that makes sense.
but it might not learn the true cause, which is the car slowing down. So what happens if the car ahead slows down rapidly, but its brake lights are broken? The AI, relying only on the learned correlation, might fail to react appropriately.
Ah, I see. It learned the symptom, not the cause.
In simple terms, yes. And to make things potentially worse, Tesla's known lack of hardware redundancy in power supplies, sensors, computing units magnifies this risk. If that single, complex black box system glitches or fails,
There's no robust backup.
not in the way you typically see in aerospace or even other automotive safety systems, it's a potential single point of failure for the entire driving control.
So, for you, our listener, this really prompts a critical question. Is a system that performs well, maybe even feels human, but can't be fully explained or rigorously proven safe? Is that system truly intelligent enough for our public roads, especially when lives depend on it?
It's a fundamental question about trust and verifiable safety.
All right, let's tackle the final piece of this complex puzzle, what we're calling the human factors gap, the paradox of monitoring. Level 2 systems, like Tesla's Autopilot and FSD, are all built on one core premise,
Right.
That the human driver will continuously monitor the system and always be ready to take over instantly.
That's the requirement, yes.
But fascinatingly, this premise seems to fly directly in the face of decades of research into basic human psychology.
It really does. This brings us squarely to the concept of automation complacency. It's a well-documented phenomenon.
Okay, what is that exactly?
Essentially, human factors research consistently shows that when an automated system works well most of the time, when it's highly reliable, humans become, well, frankly, terrible monitors.
It's not about being lazy or a bad driver.
Not fundamentally, no. It's a natural, predictable psychological reaction. Think about it. When automation takes over the demanding task of driving, it frees up our mental resources. Our brain naturally wants to shift its focus elsewhere.
Okay.
And as the system performs correctly again and again, we start to trust it more. That trust leads to reduced vigilance. Plus, humans are just inherently bad at maintaining focus during long, boring monitoring tasks. Our attention inevitably drifts.
So wait, the better the system works, the more reliable it is, the more likely we are to stop paying attention. That's a serious paradox.
It absolutely is. The system, by its very success, effectively trains the driver to become complacent.
Which means when that rare failure does happen,
Yeah. The driver's reaction time is significantly slower, and their ability to even detect the failure in the first place is reduced. They're simply not in the loop anymore.
and Tesla's system for monitoring the driver, the DMS, it has some widely criticized weaknesses in addressing this, doesn't it?
It does. Their primary method relies on detecting torque, basically, small movements or pressure on the steering wheel.
Just checking if your hands are on the wheel.
Essentially, yes. But NHTSA has explicitly called this approach a critical safety gap because it simply fails to prevent that foreseeable driver misuse we talked about earlier.
Because drivers can easily cheat it.
Easily. You can hang a weight on the wheel or just jiggle it occasionally while looking at your phone, reading, or even disturbingly while asleep. It doesn't measure attention.
So what's the alternative? What's considered best practice?
Industry best practice, and what's becoming standard, involves using in-cabin infrared cameras to track the driver's actual eye movements and head position.
So it knows if you're looking at the road.
Exactly. It can detect distraction, drowsiness, or general inattention with far greater accuracy than just checking for hands on the wheel. The European Union, for example, is already making these camera-based DMS mandatory because they recognize how crucial they are for Level 2 systems.
And the tragic toll of this human factors gap combined with the other gaps, the numbers are pretty stark.
They are sobering, yes.
Yeah.
NHTSA data points to hundreds of accidents linked to Tesla ADS systems. A Washington Post analysis confirmed at least 19 fatalities up to 2023.
And there was that specific NHTSA data set.
Right, from July 2021 to May 2022, it showed Tesla vehicles accounted for nearly 70%. That's 273 out of 392 of all reported accidents involving Level 2 ADS systems, and 5 out of the 6 fatalities reported in that period.
Wow, 70%?
Then there's NHTSA's 3-year investigation into Autopilot, crashing into parked emergency vehicles that involved 467 accidents and 14 fatalities. More recent FSD probes cite accidents and fatalities in those low-visibility conditions we discussed. The total confirmed death toll linked to these systems by NHTSA or expert analyses is now at least 44.
Those numbers are hard to ignore.
They really are. And they highlight a core insight. Foreseeable driver misuse isn't just about blaming the driver. It's often an unintended consequence of the system's design interacting with predictable human psychology. The human becomes the weakest link, not necessarily by choice, but almost by design.
Okay, so we've explored these 4 pretty significant systemic gaps. The crucial question now is, how do we bridge them? It seems clear it's not just one fix, right? It needs a multi-pronged approach.
Absolutely. It requires a holistic strategy, combining better technology, yes, but also stronger regulation and a much greater focus on human-centric design.
So let's break that down. Recommendation 1, technology calibration.
Yes. Embrace sensor fusion and redundancy. The clear recommendation is to mandate sensor fusion, combining data from cameras, radar, and ideally LiDAR for any advanced automated driving system. For Tesla specifically, this means reintegrating radar and seriously considering LiDAR.
And the reasoning is just basic physics and redundancy.
Pretty much. Physics tells us, and real-world tests like Mark Rober's demonstrate, that multi-sensor systems are inherently more robust, especially in bad weather or tricky lighting where vision only struggles. Redundancy having backups is just fundamental engineering practice for anything safety critical. Think airplanes.
Makes sense. Okay, second area, AI architecture improvement, moving beyond the black box.
Right. The recommendation here is to promote hybrid AI architectures. Combine the strengths of deep learning for pattern recognition with verifiable, rule-based safety monitors. Don't let opaque, end-to-end black boxes be the sole decision makers.
So have a safety net of understandable logic.
Exactly. This creates a safety backstop. It allows for much better verification and validation, that V&V process, because you have parts of the system whose behavior is predictable and provable. It helps prevent those catastrophic failures that purely opaque systems can't absolutely guarantee against. It's about building verifiable trust.
Okay. Third, human-centric design. This goes back to the driver monitoring.
Absolutely. Regulators must mandate effective camera-based driver monitoring systems, systems that track eye gaze and head position, not just hands on the wheel. And critically, these systems need to be designed to actively combat automation complacency, perhaps through more adaptive alerts or interventions.
And the reasoning is clear from the research.
Overwhelmingly clear. Camera-based DMS are simply far superior at detecting driver state distraction, drowsiness. The current torque-based systems are a known significant safety flaw, as NHTSA itself has pointed out multiple times. The EU is leading the way here by making camera systems mandatory.
Right. And finally, the fourth area, regulatory and communication reform, truth in advertising.
Yes. This is crucial. Regulators, like NHTSA and the FTC, need to strictly enforce truth in advertising for these systems. Prohibit misleading marketing terms like full self-driving for what are clearly level 2 driver assistance systems.
Set realistic expectations.
Precisely. We also need standardized, easy-to-understand labels for consumers, maybe like energy efficiency labels, but for automation capabilities and limitations, and pair that with widespread public education campaigns.
Why is that so vital?
Because clear communication is fundamental to safety here. The current confusion caused by marketing terms directly leads to misuse and over-reliance, which, as the accident data shows, has tragic consequences. Setting correct user expectations from the start is paramount.
Okay, so just to quickly recap for everyone listening, we've identified these 4 interconnected systemic gaps. The terminology gap, confusing drivers, the sensor gap, limiting perception, the AI's common sense and interpretability gap, hindering reliability in novel situations, and the human factors gap, where system design clashes with human psychology.
And it's crucial to remember, these aren't just minor software bugs to be patched. They represent fundamental challenges related to design philosophy, hardware choices, the very architecture of the AI, and our understanding of how humans interact with automation.
So the path forward to genuinely safe automated driving It isn't just about chasing smarter AI or making it drive more like a human.
Not solely, no. It demands a shift towards a more rigorous, safety-critical systems engineering approach. Think robustness, redundancy, verifiability principles applied in aerospace for decades. Every component, from sensor to software to the human interface, needs to be designed with safety as the absolute priority.
Which brings up an important question. What does true intelligence really look like when we're talking about safety on the road?
That's a great question to ponder. Is it just a system that drives smoothly like a human most of the time? Or is it a system that is inherently safe by design, predictable, verifiable, and resilient, especially when faced with the unexpected? Achieving a 100% safety might be unattainable in complex, real-world driving. But closing these fundamental gaps, ensuring robust perception, understandable AI, effective driver engagement, and honest communication, that's the only viable path toward making automation reliably safe for everyone on public roads.
So here's a final thought for you to consider. As these technologies continue to advance and become more common, what is your responsibility, not just as a potential driver or passenger, but as a citizen, in demanding clarity, accountability, and verifiable safety from the companies building the vehicles of the future?